Thank you for joining this webinar about the challenges in heat exchanger and pressure vessel today. And my name is Dat Huang, and I am senior CFD engineer of DFE-Tech. I have 10 years of experience in this engineering simulation industry. 4 years at Denso, which is the biggest Japanese automotive tier 1 company, and 3 years at VinFast. VinFast is actually the startup company in the automaker industry, and now they are focused on electric vehicle. And I have another 3 years working as Ansys channel partners to introduce and promoting Ansys product to the Southeast Asia market. Today, I would like to guide you through the key practices in using simulation tools to optimize heat exchanger design and enhance performance. Okay, so to begin, let's look at some of the significant challenges here that we might face when we operate heat exchanger. These challenges are critical to understand as they will set the context for why advanced simulation techniques are necessary. Heat exchanger faces several significant challenges in operation, such as optimizing heat exchange efficiency while minimizing the area, or operating under harsh conditions like frequent cold and hot cycle, and reducing power consumption and the overall operating cost, and ensuring system performance, and also proper sizing to fit with the system, and also commissioning and controlling the system effectively. So let's keep these challenges in mind, then we will move on to see how simulation impacts the design and development process. And actually, simulation today plays a very crucial role in overcoming challenges by leveraging simulation. We can achieve remarkable improvement in the performance and efficiency. For example, here we have some example, like we can gain up to 20% of efficiency in potential active volume with minimal design modification, or we can increase 15% in thermal capacity with significant cost reduction. So these numbers actually highlight the transformative power of simulation in heat exchanger. And to achieve such significant improvement, we need a robust set of simulation capacity capabilities. I hope my my voice not so so much people.
Mr. Dathong, I think your mic got a little bit with the echo. If you can adjust a little bit, or probably because of the space, it will be even better.
Okay, sure. 1 second. I try to change my microphone setup. Maybe because of the noise cancelling. Let's see here.
Yeah, let Mr. Dathong to switch his position a bit, so we all can have even better voice effect.
Yeah, sorry for the interruption, because I think because of my laptop noise cancelling setup. So try to answer. I hope it's more clear now.
A little bit better. A little bit better now. Yeah.
Better, right?
Yeah.
Yeah. Okay. Thank you. Okay, I share my screen here. Okay, so we come back to some of the simulation, advanced simulation capabilities we need to achieve the outside requirements in the heat exchanger design. So here we now need to have multi-scale, multi-phase, multi-domain, so multi-physics simulation, and we need to have tools to optimizing the diffuser shape and the tube thread shape. Yeah, so each of these will be a separated session in the following slide. So we'll talk about it later, but I just want to highlight here the capabilities. And we need to have the conjugate heat transfer, which means we need to involve fluid and solid heat transfer in just one simulation. We need to consider the cold and hot cycle, fatigue analysis. We need to consider the condensation and evaporation phenomena happening inside the heat exchanger to capture correctly the efficient and the performance of the heat exchanger. So let's dive into a specific case to illustrate these points. So the first case will be the diffuser shape optimization. Okay. So in this specific case study, I would like to put here some engineering challenge when we want to do the diffuser shape optimization. It includes the achieving uniform distribution of the hot fluid into each tube, which means we want to have uniformity of the flow. And we want to reducing the non-uniform cooling and stress distribution on the end plate. And also we want to minimize the pressure drop. So all these things we need to consider a lot of design option, or we call here design point. And to evaluate every single design point is take a lot of time. So we need to have a specific method to come up to work with, to deal with such complex and huge problem like this. So for Ansys, we have some specific tool to address the challenge. So we have Ansys Fluent that some of you might familiar with to do the heat transfer modeling. It's very accurate, and now with a lot of improvement, we can do it very quick, easy, and also it's had very familiar user interface of the software that way, which I will show you later in the demo session. We also have Agile Solver. So you might know Agile Solver, which is for the sensitivity analysis and the topology optimization. So it's very powerful optimization tool inside Ansys Fluent. And also we have Workbench. So like Dr. Hazim just showed you, that Workbench is a comprehensive platform to organize and to do parameters study, to do DOA optimization. So we have Workbench, the platform for all simulation. And we also have some other like fast pre-processing tool. Now we have Spacecraft. Maybe you in the last several version of Ansys, maybe from version 17, 18, we have Spacecraft, which is very powerful and easy to CAD modeler and also CAD preparation tool. And we have Fluent Meshing also improved a lot from some previous version that can do very well polyhedral or even hybrid mesh for CFD profit. And also one of the very important thing that cannot miss from any huge problem, simulation problem is scalability, the HPC problem. So Ansys support very well with scaling of the parallel computing. So with good number of cores, and then with the good performance of the HPC system, and with the Ansys solver, we can run the simulation very efficiently parallel. So now we will look closer to the shape optimization case here, where we have the one of the sample here, one of the heat exchanger, but we only focus on the diffuser reason, just to make it simple here. So they just focus on this shape. And the target here is to maximize the flow uniformity at the outlet here, okay, and minimize the pressure drop of this region. So to make it simple, they just consider the outlet region only. Of course, we can consider the whole design here, but it will take more time and effort. And we consider 3 parameters here. The parameter 1 is the length of this dimension. Here is the just, I'll say, the first inlet of the diffuser, and then here is the radius of the band here, the parameter 2, and the parameter 3 is the width of the inlet. Yeah, so we will use these 3 parameters in the optimization process. And to do the optimization here, we employ the Ansys workbench and the DOE, the design of experiments. We can study here many design points with 3, I'll say, input parameters and 2 output parameters here. So you can see here in this example, they have 13 design points. And by using this DOE and the responsive place, one of the optimization algorithm here, in Azure, where we can systematically explore all these design points. And with all of these things, we come to a very significant improvement that we can improve 20% improvement. We can achieve 20% improvement in the uniformity, and also very good reduction in the pressure drop. So here is the final the optimized shape. We can see much different from this initial one. Right? So here is the optimization one. Okay, and now we will shift to another critical aspect. Is two-thread shape optimization also very, I would say, critical aspect here to affect the performance of the heat exchanger. And in this optimization topic, we also face a lot of very significant engineering challenge, like we need to design the groups. Right? The groups is on the tube, on the heat exchanger tube, to enhance the heat exchanger performance. We also need to managing the group depth and the pitch, so that they can effect effectively on the turbulence flow and the heat exchanger, right? And For Ansys, we have spaceplane and fluent meshing that can work very well with such small features. A very fine feature like this, we can small. So I can show here some very fine feature. Like here we have the tubes and we have the groove that is normally very small, few millimeters like this. And also we have some kind of parameter like pitch. We have can simulate or we can model different pitch distance here, and it can be captured correctly by the space plane, Ansys space plane, and also Ansys meshing. So here is one of the I would say demo showing how the fluent meshing can easily represent the correct shape of such a small picture like this, the group, and also these parameters. So he takes something here, not only the group itself, but also the thickness of the group. As you can see here, if I can zoom in a little bit, you can see we can have such thin color meshing to capture the very thin thickness of the tube here. So this is very helpful, very useful to do further CHT, the conjugate heat transfer simulation later, where we need to have very good, how to say, mesh quality. For example, here the mesh quality here we can have quite well 0.8 0.88 unit. We have poly cells, so it's very good for the conversions and also save a lot of mesh now. Right. So this will very well for the later this heat transfer, the conjugate heat transfer simulation. So for the heat transfer simulation here, we will try to understand the thermal performance of the heat exchanger, and we can use the model, the mesh built from the previous tool like Ansys space plane or Ansys Fluent. And in this conjugate heat transfer problem, actually, is also has some very significant engineering challenge that we need to have suitable tool to capture it, to deal with it in simulation. So then here is to finding the effect of pulling flow rate. For example, we have different number of flow rate. So we need to study which is the most suitable flow rate. And the thermal load also, and the pressure drop. And also sometimes we need to handle it with the complex turbulence problem. And even not steady problem, but also transient problem also. So here we have Fluent. So Fluent can deal with steady, can deal with transient very well, can deal with 2D, even 3D. Sorry, can deal with 3D and even 2D. So now even 2D meshing is supported in Fluent meshing. So because you cannot do 2D meshing or in Fluent meshing, we just can do with Ansys meshing, but now it also supports in Fluent meshing. And we have a single workflow. Single flow means all the things you do is on a single Windows. We from meshing to solver to post processing all in just one Windows. Okay. So here one example of using the Ansys meshing workflow, but we also have Fluent meshing workflow. So I think some of you guys, if working with Ansys, very familiar with Ansys meshing, we can do full domain meshing, solid domain matching, we can do the to create the contact between or interface between Fluent and solid. We can have conformal or non-conformal interface, but all of them supported. And now we can use Ansys, Fluent matching with much easier workflow. So okay, here's some setup. I'll just skip it. And here is some example on the result that we can have, like when it's a CMD post, so very easy to use. You can export the heat, the temperature, the flow, velocity, or the pressure. Very easy, so you can easily evaluate the performance of the heat exchanger. Going to next topics for the particular analysis, maybe it's more like structural problem, but I just want to give some insight here on how cold and hot cycle will affect the fatigue, and then we can use CFD here to support the evaluation. So just give some similar to previous topic. Let's give some engineering challenge, like we need to estimating the life of the heat exchanger under some harsh condition, like the cold and hot, the frequently change cold and hot cycle, and we need to performance the mechanical and structural thermal analysis. So the solution here from Ansys is for fatigue analysis is Ansys encode design life. So encode is very famous, even in other, not in this manufacturing heat exchanger, but in other industry like automotive, very famous and well widely used by many OEM companies in the world. So we have Ansys encode design life. We have the system coupling to coupling the fluid and structure analysis in Workbench. So we can do the I would say FSI or one-way, two-way simulation. So it's very easy to solve complex simulation in Ansys Workbench. And here is just the I would say some example on the result here. Thermal structure analysis is one kind of the I would say coupling simulation here. So we have the temperature imported maybe from CFD or from other thermal analysis, and we add here, and then we can calculate the stress, and like due to the stress due to the differential of temperature on the structure. And it can be used later. The stress result here can be used later for the encode design life calculation. Okay. Here's just some result on the stress. And then we can put it here the result from stress analysis to the design fatigue encode design life fatigue analysis here. So we have the result as the FE result file here from mechanical, and then we have the maybe the SN curve setup, or we have the cycle duty cycle setup, and then we can perform the fatigue analysis and get the result like this. So we can see how many cycles the device can, or the equipment here can withstand. Okay. Yeah, so just some detail of the side of the work process. So here, for example, the result is showing that it can we said with minimum 6.5 million cycle. Very good design here. Okay, and some kind of system coupling, CFD and assist mechanical coupling simulation to show the capability of Ansys to perform multi-physics simulation here. So we use Ansys Workbench, and then we can coupling between CFD, which is Fluent here, and then mechanical simulation. Okay. The last one here is the condensation evaporation, which is related to the multi-phase flow simulation, and a lot of complex physics here, which is boiling and condensation here. So this one will affect very, I'll say, significant on the performance of the heat exchanger. So we need to managing the boiling and the condensation within the heat exchanger. So we will not make it happen to, how to say, too quickly or too much. That will reduce the performance of the heat exchanger a lot. So we have to perform such a multi-phase problem. We have Ansys Fluent. Ansys Fluent have very good condensation and evaporation model, and also boiling model. Or even semi-mechanical boiling model also there to capture correctly or accurately the phenomena. And here one example of I'll say using the semi-mechanical boiling model, that we can, for example, here capture the heat exchange happening, and then capture the some of the, like the heat flux here, for example, through the area. So it's one of the how to say reduction model to just capture the phenomena, but we can also go with more how to say more complex problem. Like here we have we really capture the evaporation and condensation here with how to say we have the mixture here. Cooling agent is ethylene glycol, and we try to capture the evaporation and condensation phenomena happening inside with this material. And here is some example. For example, we can capture correctly the temperature happening inside. Well, and then we can capture the vapor or the evaporation happen. So, for example, where we have very high temperature, we can see the vapor, the glycol here happening from the evaporation. All right. And also capture the condensation happening in the cold cycle. Yeah. So just give it's all for some of the very how to say challenging topic we might face in the design and how to say optimize the heat exchanger. So in conclusion, I can say that using such advanced simulation techniques like Ansys here we can significantly enhance design performance and also the durability of the heat exchanger. And by addressing these challenges with a comprehensive simulation approach, we ensure the efficient and reliable heat exchanger operation. So that's what I want to give you here today. And the next session will just a simple demo from Ansys that I want to show you how while Ansys Fluent now can support you in the heat exchanger and heat exchanger design and optimization. So here is one of the very I'll say common heat exchanger design where we have the louver fins. So we have multiple louver fins and we have the couple tube. So inside each tube will be the hot fluid. And actually here we have external, we have the airflow to cooling the hot fluid inside the tube here. And in this simulation demo, actually the fluid inside the couple tubes here will not be presented. Just to make it simple, we just put here like a convective power condition on the wall. And then we try to capture correctly the airflow through these fins. Also, the heat transfer parameters between them. Okay. And here is software. We open the software. Okay, so here is the model that we can use in the simulation. So again, this is this by the mouse. Okay, so here is the model. Look quite simple, but actually we can capture very detail the inside. So for example, here, if I add something. Okay. Okay. So you can see here, actually inside, okay, so you can see we have some pins, some plate like this inside. This one is just to try to mix the flow layer from from bottom below to upper, lower to upper part, so that can increase the I'll say the mixing of the between the hot and cold flow, so can increase cooling efficient here. So actually, we try to capture correctly the flow characteristic through these fins. Okay. And actually, we have multiple layer. So to simplify the problem here, we put some kind of periodic condition here on this phase. On this phase, we put periodic condition so that we can simplify more the problem. And I will show you the mesh, how it look like. Okay, so if we look into this, you can see that we have polyhedral mesh here, and we capture very well the how to say boundary layer showing the fins, and also for the inlet and outlet part, we can use the extrude mesh here, extrude mesh, so that we can save mesh count with extrude mesh. Okay. So you can see all the details how the prints can capture very well with polyhedral mesh here. So actually, in such problem, we can have multiple zone with multiple mesh type, and we can have like non-conformal interface between them, like this. Okay. So here's for the mesh, and now here in Fluent, we can do the post processing very how to say easily, and also can capture very well the flow. And even if you want to do something like look beautiful, you can do like this. So something. Okay, so some screen. Okay. Okay, so here we can do some colorful thing. It's good for understand the flow physics, and not only engineers, civil engineer, but also some kind of like managers or even design engineer also can have some idea based on this result. You can see how the flow looks like and have some idea how to improve the flow. So even we can do some kind of animation here. So, uh, so it's give us the result looks very how say easy to understand how the flows really look like. And you can see here that we have, because of the how to say multi-layer, so actually output will try to move up. So some of the food will from the bottom layer will move up like this to mix with upper layer. So that will increase the heat exchanger, sorry, heat transfer efficiency. Okay. And that's for some kind of beautiful things. But for technical things, we can export any kind of common, how to say, CFD result like pressure. You can give it, you can get it like this. So to evaluate the, for example, heat pressure drop, for example, right? And temperature, you can get it very easy. And temperature on surface, on plan, and many other problem can, many other result can be captured, can be exported from the software. So you can get whatever you want, vectors, contours, velocity, for example. Right? Yeah. So we can have something like this. Okay. Or even vectors. So now you have many choice to do the post processing. You can do it in CFD post. You can do it in Fluent directly. So yeah, we can see it. Example, yeah, you can see the flow direction very clearly here. Okay. So yeah, that's all from my presentation, and thank you for your attention.